Well, here we have an exam question from Aston University, and it's about stochastic time series. So for the first question, we have to define the weak and strong stationarity, and the answer is of course a part of theory, and we know that the process is stationary if the statistics of the corresponding time series do not change over time. It means that a process is weakly stationary if the first and second order moments of the process are both finite and do not depend explicitly on time. Now, mathematically, we can define that as mu2, or expected value of xt, is less than infinity, so finite, and mu2 is constant, equals to mu0, and gamma tk, that's the expected value of xt is less than infinity also. And again, gamma tk equals to gamma k, so you understand that this expression here is independent of k. Now, what's strong stationarity? The joint distribution of xt1 xtk is the same as the joint distribution of xt1 plus tau up to xtk plus tau. Equivalently, we can say that all moments of this stochastic process are finite and independent of time. That's the answer to the first question. Now, for the next question, we consider the definition of the autocorrelation function rho of tau as a function of the lag tau of the time series process, and I want to show here that the absolute value of rho of tau is not more than 1. There's a hint in this question to use the fact that the variance of lambda 1 xt plus lambda 2 xt plus tau is greater or equal than 0, and then use different values for lambda 1 and lambda 2. Actually, the proof of this part reminds me of the proof of Cauchy-Schwarz theorem, since we use an identical logic here. So, since the variance of lambda 1 xt plus lambda 2 xt plus tau is positive, since variance is positive anyway, then we can expand that expression here, and we have lambda 1 squared variance of xt plus lambda 2 squared variance of xt plus tau plus 2 lambda 1 lambda 2 times the covariance of xt plus tau must be greater or equal than 0. Now, it happens for all the values of lambda 1 and lambda 2. Since every one of the values is valid here, I can choose the values of for lambda 1 equals lambda 2 equals 1. If I substitute here and here, of course, and here, I get that 2 sigma squared is the variance of xt, plus 2 the same is the variance of xt plus tau, since they have the same variance, and this is 1, this is 1. I have sigma squared plus sigma squared, 2 sigma squared, plus here I have 2 times 1 times 1 times the covariance, so 2 times gamma of tau, that's the covariance here, and it must be greater or equal than 0. From this one I get that gamma of tau is greater or equal to than minus sigma squared. Now we can substitute other values for lambda 1 and lambda 2, so take lambda 1 equals 1 and lambda 2 equals minus 1. Then again substituting here, we have 2 sigma squared minus 2 gamma of tau greater or equal than 0. From here I get, you understand why? I substitute lambda 1 with 1, lambda 2 with minus 1, this is 1, this is 1, sigma squared plus sigma squared is 2 sigma squared, and here I have 2 times 1 times minus 1, so minus 2, this is gamma of tau, and I have that expression here. I solve for gamma of tau, and I have gamma of tau is less than sigma squared. So I have gamma of tau divided by sigma squared, that's greater than minus 1, and I have gamma of tau divided by sigma squared to be less than 1. Again, putting these two together, we have minus 1 less than rho of tau less than 1. So this is equivalent to absolute value of rho of tau is less or equal than 1, and this part has been proved. Now for the third part I have zt, that's a process with expected value of zt equals 0, expected value of zt square equals to sigma squared, that's finite, and I'm taking s0 equals 0 and st equals z1 plus z2 plus zt, and that's the mathematical model for a random walk. I want to show that this process here, the random walk, is not weak stationary. So let's find first of all the expected value of st. This is the expected value of z1 plus z2 plus, and from properties of the expected value, but each one of them here is 0, so the sum is 0, 2. What we found is that the expected value of st is 0, so it's independent of time and finite too. Now we want to see variance and covariance. For the variance we get the expected value of st squared, and that's the expected value of z1 plus z2 plus z t squared, and that's the expected value of z1 squared plus the expected value of z2 squared plus the expected value of zt squared plus 2 times the sum of expected value of zi, zj for all the couples ij where I is less than j. But this one here is 0 because zi and zj, if I is different than j, are independent variables. So the expected value of zi times zj equals to e of zi times e of zj, and since each one of these is 0 from hypothesis, so all the sum here is 0. Yes, but we know that the expected of z1 squared is sigma squared, and since they have the same distribution, have sigma squared for each one of them, so it is t sigma squared. Also the covariance, let's see the covariance. The covariance is gamma of t plus h comma t, and that's the covariance of st plus h st. That's the covariance of, since we have st plus h, it's st plus all the terms from st to st plus h, so zt plus 1 plus zt plus 2 plus zt plus h, and we have st here. From a property of covariance, we know that we can break this one here into couples st, st, zt1, st, so we have covariance of st, st plus covariance of zt plus 1 st plus covariance of zt plus h st. So you know that covariance of st, st is the variance, so this is ts squared, and each one of these is 0 because zt and st are independent, so all this sum here is 0, and we have t sigma squared. So the random walk is not stationary, since covariance and variance are functions of time.